Welcome to my long ISP, the Nixie Gecko. This is a clock meant to look and function like the popular Gecko made by the ASUS program, with the main difference of 4 retro IN12 Nixie tubes that replace the modern 4-digit 7-segment display. It can also be controlled through an infrared remote. Before explaining the complexities behind driving these Nixie tubes, I'll first go over the features. Similar to the Gecko, the Nixie version consists of several PCBs and an acrylic plate to top it off. It displays the current time, date, year, temperature and humidity, and is powered through a 5-volt micro USB or a 5-volt power jack. It can also be switched off using the power switches. Other buttons and switches on the PCB allow a user to customize the clock in various ways, unlike the original Gecko. The mode button cycles through the different displays, and flipping the edit switch allows a user to configure the clock. Here they can change the time using the increase and decrease buttons, and the mode button switches what sets of digits are being changed, while the large snooze button goes the other way. You can also edit the date, year, and alarm by scrolling through the mode and snooze buttons, or by flipping the edit button to put the clock in normal mode, and press the mode button to cycle to the specified mode you want to change and flip the edit switch. When doing this over the temperature/humidity mode, the alarm can be changed. Here I've got it set to 7 o'clock, but to demonstrate its functionality, I'm going to change the alarm 1 minute ahead of the current time and flip the switch to turn on the alarm and now wait. So as you can hear, once the current time reaches the alarm time, a buzzer goes off. It can be snoozed by pressing the snooze button and will currently only snooze for 10 seconds. This will be changed to something like 5 minutes, but I set it to 10 seconds to demonstrate its functionality. Once it goes off again, you can snooze it for an indefinite amount of time, or do what I usually do and turn off the alarm using the switch if you don't want to get out of bed. Also, you may have noticed the third switch without a label. This is because I didn't yet know what to use it for and currently still don't really know. So for now, it changes between 12-hour and 24-hour time. To differentiate between AM and PM, the debug LED on top turns on when the time is in PM. As in the name, the clock can also be controlled through an IR remote. Here I've got one on a breadboard where the first two buttons simply change modes. These are pretty basic and I plan to add more features in the future, but I was running out of time before the deadline, so this is all I've got so far. Now I'll move on to how it works, starting with the Nixie tubes. These work by running high voltages to the anode and through the different stacked cathode digits to ionize the gas around them, producing light. With this comes a problem called cathode poisoning that arises from leaving one digit on for too long, where excess material from that digit spatters onto surrounding digits, blocking the emitted light. Fortunately, this is easily and fancifully solved through iterating through all the digits periodically, as you may have seen in my demonstration. Now, these voltages required needs to be at least 170 volts DC, so you gotta be careful. To achieve such voltages, I use the boost converter, which on the most basic level stores up energy in an inductor and pumps it into a capacitor, converting 5 volts into 170 volts. Here I've got two versions, one which I built and the other which I bought. Either one works with a Nixie clock, though the one I bought maintains the required voltage a lot better than mine. Now, to actually display different digits to show time and other data, we have to take a look inside by removing the display PCB, revealing the circuitry. Here, an ATmega 328P takes in data from a real-time clock and a temperature and humidity sensor. This data is converted into bits that the shift register reads and outputs, where it controls the Russian-made K155ID1 and 4 high-voltage optocouplers, which are similar to transistors. The Russian IC was made specifically for driving Nixie tubes. They take in a 4-bit binary input and allow current to pass through the converted decimal number assigned to one of the pins. Since one IC can only control one tube, the 4 octocouplers each control a tube's anode to multiplex them where only one tube is on at a time, utilizing the persistence of vision effect. The high voltage is generated at the back through switchable boost converters that line up with the female headers. This high voltage is passed through the aforementioned optocouplers and then passed through current limiting resistors to be fed through the female header, where they power the anodes of the tubes on the display PCB that fits on top. The cathodes are then routed from the tubes on the display PCB into the female headers at the bottom and towards the K155ID1. The rest of the components on the base PCB help configure the clock or simply make noise. On the IR remote side, a button array connected to an R2R ladder outputs different voltages depending on what button is pressed through this configuration. It allows a single analog pin to read the output and decide what IR signal to send out to control the clock. I was planning to create a PCB for this but didn't have time to. Speaking of PCBs, the ones that were designed had high voltage considerations. Examples involved widening power traces and trace widths to prevent arcing and to make traces as short as possible. This is especially important in the boost converter PCB, which is why a ground plane was added, as any stray resistance affects its efficiency and its ability to maintain output current and voltage. After receiving them and soldering them up, there were a few major issues present, but luckily they were fixable. Firstly, the microcontroller was always in a state of reset because the ground and power traces were reversed, so this required some cutting and rewiring for the clock to function properly. Secondly, the digit cathodes on the display PCB were mixed up with the base, so different digits would light up from the specified binary input on the K155ID1. This was solved through creating an array that would light up the corresponding binary inputs to the correct digits. Other minor issues include the buttons and switches being hard to reach and some spelling errors, which will all be fixed if I ever make a second version. All things considered, I'm very proud of the result and I'm super glad it works, as I've been wanting a Nixie clock. In the future, I definitely plan on adding more features and experimenting around, as I didn't have much time to over the week. So far though, I've tested it a few times and can tell you that it functions perfectly as a clock to help you keep track of time when working on a long project, or a bedside clock to help you wake up in the morning. Unfortunately, these tubes aren't widely produced anymore. Most come from eBay, where Eastern European countries sell off old stocks, but they've recently been making a resurgence in production with companies such as Dalibor Farnese. All of his Nixie tubes are expertly handcrafted and look wonderful. I highly recommend taking a look at his YouTube channel. There are also many enthusiasts making clocks and other devices with them. One such person is Mariano Elia, a former ace who created and developed the Enix Nixie clock and who I'd like to thank, as he provided me with his tips and tricks on handling Nixies. I also recommend checking his website out to help support him and his company, Argon Prototypes. Anyway, that's my long ISP, the IR Nixie Gecko, a clock made from the experience of being in the ACES program for 2 years. Thank you for watching, and it has certainly been a fantastic couple of years.